introduce Ali, who will talk about the weak tracial approximate representability for actions of finite groups on C-star algebras.
Okay, thanks a lot for the introduction. I'm so honored to be here in Prague in Karen's research group. And also it's really interesting to talk here in person after a while. So today I'm going to talk about weak tracial approximate representability for actions of finite groups on C-star algebras. So we are going to start with some background information. But to start the background information, it is necessary to recall some definitions, some notation, etc. Okay, let's start. Throughout my talk, A is unital C-star algebra, and also G is a finite group, and alpha from G to automorphism of A is an action, and we usually actually write this notation for that to just simplify notation. And if now let alpha be an action of G on A, an action, then we denote C-star G, A, and alpha by the cross product by alpha. Okay. We also denote A alpha, the fixed point algebra by A alpha, and A alpha means all A in A, such that alpha G of A is equal to A for all G in G. So now, as you know, if we have a abelian group, then the Pontryagin dual is also a group. So, and therefore we can define an action of that Pontryagin group on the cross product. So if G is abelian, finite, not necessarily finite, but abelian group is enough group, then the dual action alpha hat from the dual act, the Pontryagin dual of G to automorphism of C-star of G, A, alpha, and this is notation for cross product, is defined by, okay, alpha hat sigma of AG UG. Okay, and here we should assume that G is a discrete group. AG UG is equal to sigma G or AUG. And AUG is just elementary elements of.
Are we assuming G or G hat is the discrete group?
G hat.
Okay.
Yeah. Okay. Yeah. But you know, we are going to work with a finite group, so in this sense, so it doesn't matter. For example, whether it is, I mean, as I said throughout all my talk, G is finite, but the Pointryagin dual can be defined for abelian group, so never mind about that. So now, okay. As you know, duality theorem duality theorem plays a very important role in many branches of mathematics, and in particular, the study of group actions. So, namely, here I have a duality theorem. Okay, and here we have an action of finite group on a unital Tracial algebra, and also like alpha, and our group is also abelian. And here we have alpha hat. So if we have an action of a finite group, finite abelian group, and if our action has a Rocklin property, then the dual action is approximately representable. Or here we have approximate representable. So, and if, for example, here we have Tracial Rocklin property, and here the dual action is tracially approximately representable. Okay. Tracial approximate representable. We also, if for example, if we have a Rocklin dimension then here we have a representability dimension. Okay, very roughly speaking, duality theorem says that if our action has a property which is close to alterness, then the dual action has a property which is close to innerness. And I will define all these definitions: Rocklin property, representability, tracial version of that, and weak tracial of that precisely on my talk later. But just now, here, if we have an outerness, then the dual action has an innerness and vice versa. So, and now here we have a notion under the name weak tracial Rocklin property. So the analog of weak tracial Rocklin property is no, but here we need something. We need something here, and here we need the analog of innerness here. So, and this definition, or this object here deserves to be called weak tracial approximate representability based on this table. So whatever the definition is, so I will precisely give you a definition later. So, and now we are going to talk about this definition also. And if you have this property, then if I have time, I will talk about the cross product by sort of action and then radius of comparison of those actions. So, okay, let's start with definition of Rocklin property. Where is the eraser? Okay, I think that I have. We still have one blank. Okay, definition. Izumi 2004. So let alpha be an action. And the action alpha has the Brooklyn property, and we abbreviate it to R dot P. If for every epsilon bigger than 0 and every finite set F in A, there are projections e.g. in A for G in G such that, okay, such that number 1, alpha G of EH close in norm to EGH. And this is basically means the norm of alpha G EH minus EGH is less than epsilon. So I use this notation there. Number 2, alpha AEG, and here for all G and H in G. Number 2, AEG is A commutes approximately with EG for all G in G and for all A in F. And number 3, the sum of EG, G in G is equal to 1. Okay, let's draw a graph to illustrate what I'm saying. Okay, now I need to. Yeah, go ahead.
So you mentioned this n-ness, or maybe the other way around, outness there and n-ness there. Could you explain why one might expect that to be the case?
To be the case of
why outness on this side should correspond to in-ness on this side of the dual action.
So yes, it's common. I mean that it is a notion that we can even generalize it to quantum group. So if we have a outerness here, but not outerness, a version of outerness, and this is namely Rocklin property or a version of Rocklin property, then we have a version of innerness here. If we have a sort of projections here, by those projections we can construct unitaries here, and those unitaries provide a version of innerness for us. And if we have a unitaries here, then we can average them on the cross product, and then we can find Rocklin projections. So that's why I said that which is close to alterness, because if you have a Rocklin action implies the alterness, but the other one is not true. So yeah, I don't know, you get your answer. Yeah. Okay, let's draw a picture here. Okay, for simplicity, take G to be Z mod 5Z, and think of C of X. Okay. In Rocklin property, we have something like that. 1, 2, 3, 4, 5. Here we have X. Here 0, 1. I need different colors. Here is E0. Here is E1. Here is E2. And here we have E3. And one more color, which will be this. And here we have E4. So if you want to visualize what I said in the definition of Rocklin property, it is, I think, that sort of quick graph that you figure out what's going on in this case. We have sort of orthogonal projections. And in the Rocklin property, the sum of projections is equal to 1. So, but in the version of Tracial Rocklin property, so the sum of projection is not equal to 1. So we have a small piece here, and therefore we have something extra here, and this is called 1 minus the sum of EG. G in G. So in this is for this should be smaller. So, and this is for a version of Tracial Rocklin property in this case. And okay, let's also draw a picture for weak Tracial Rocklin property now, and then I will give you a appropriate definition of this Tracial Rocklin.
Quick question.
Yeah.
What's the difference between, in this case, couldn't you just say E5 minus EG, and then you just have the Rocklin property with 5 projections instead?
Yeah, those are okay. X should be sort of a specific, I mean that this is not connected. For example, you can take X to be closed interval 0 and 2 and union, for example, I don't know, 4 and 5. Then your E0, for example, in the case of Z mod to Z, E0 is a characteristic function on this interval, and the other one is characteristic function on this interval, and the sum of those things is equal to.
But I mean, my question is that, okay, in this picture you've drawn,
yeah,
just call E5 equal to 1 minus EG, and it seems like then you have the Rocklin property with respect to now 6 projections instead of the 5 you have there. Does they still add up to 1? So what's the difference? So
in this picture, okay, the projection comes from the cardinal. I mean that the number of projections comes from the number of group. So I mean that the cardinal of G. So and G is finite, so therefore we have we can only find 5 projections. And also, you know, the projections are supposed to have this situation. I mean that alpha G of one of them should be the other one. So I mean that alpha G of this sort of projection should be the other one. So I don't know whether you get your question, the answer, or not yet.
So what happens when you apply alpha to E4?
Alpha is equal to B4. So it is, because our group is cyclic, it is equal to E0.
Okay, so alpha just doesn't go near this 1 minus EG?
Yeah. Okay. So in the case of Rocklin property, or in the case of Tracial? Yeah, in the case of Tracial, no, this should be a small in trace. So if I want to say precisely, it means that the trace of 1 minus sigma of EG should be a small, less than epsilon. And that's why I draw a very, very small piece of things here in comparison with these parts. Yeah. Now, okay, let's call this one. Okay, now in weak tracial approximate, in weak tracial Rocklin property here, instead of projections, we replace positive contractions in this sense. Okay, here we have map. Okay, here we have X. Here we have 1, and this is. So now we have F1 here, F0, for example. And then we have F1, okay, not necessarily in this. Oh, you can make a space here. Here we have F1. Here we have F2. F3 here. F3 here. And F4. F4 and F4, and here we have also F1. So F0 is complete part of this shape. But here, because in tracial Rocklin property, this part is small, but in the weak tracial Rocklin property, these parts and also these parts and this one, for example, call it delta 0, delta 1, delta 2, delta 3, delta 4, and delta 5. And then if take delta, the union of delta j from 0 to 4, then the measure of delta is small in the weak tracial Rocklin property. Okay, this is just a graph, and you do know that tracial Rocklin property and weak tracial Rocklin property is only defined for a simple Caesar algebra, and now it's just a rough picture of what we are going to say. So, and I will define precisely what those definitions are. Okay. Okay, the simplest example of Rocklin property is just example. Example 1. Let alpha be an action on zima to z to automorphism A directs on A. It's just a flip action. Oh, okay. Alpha in B is equal to B and A. This is the most immediate example of Rocklin property, and the Rocklin projections are 0 and 1 and 1 and 0. So now definition. Izumi 2004. Let alpha be an action of G on A, an action. We say that alpha is approximately representable, and just abbreviate it to approximate A.R. if for every epsilon bigger than 0 and every finite set in A. Now there are unitaries Vg in U of A such that, okay, number one, alpha G of A is close to ZG A ZG star for all A in F and all G in G. Number two, okay, I need to erase. Number two, ZG ZH is close to ZGH. And number three is alpha G of ZH is close to ZGH G inverse. Here for all G and H in G, and here for all G and H in G. Okay. So this is the definition of approximate representability, which was introduced by Izumi. So now, theorem. Okay, maybe I can provide the example and then go to the theorem. Example. Let alpha be the action, generated by infinity tensor product of add of this matrix 0, 1, 1, 0 to infinity on to infinity UHF algebra, and alpha number one, alpha has the Rocklin property, and number two, alpha is approximately representable. So this is just an example that the action simultaneously has the two property, Rocklin property and approximate representability. Okay, theorem. Theorem, again, Izumi, 2004. So let G be a finite abelian group, and let alpha be an action of G on A. Then number one, alpha has the Rocklin property if and only if alpha hat is approximately representable. And number two, alpha is approximately representable if and only if alpha hat has the Rocklin property. This is what Izumi proved in 2004, and then many people are trying to generalize this theorem in much more general setting. For example, in 2015, Kodaka and Teruya defined a version of approximate representability and Rocklin property for finite dimensional quantum group. And then in 2017, if I remember correctly, by using different definition, the work of Izumi is generalized to the setting of co-exact compact quantum group by Wallach, Szabo, and Voigt. So, but here is a problem. As you know, Rocklin property is rare, and many interesting CSR algebras admit no action of Rocklin property. So we need a replacement. So the right version of Tracial Rocklin property for non-finite compact group is not known yet. So, but however, fortunately, actually, so in the setting of finite traceability in 2018, provide a definition of Tracial Rocklin property, and then generalize this theorem. I mean, the theorem of Izumi in the setting of Tracial Rocklin property. So now let's get into the definition. Okay. I think that it's a good idea to write this definition here. Sure.
Example you have below there, how special is it for this action to have both properties simultaneously?
Okay, so here is an interesting thing. So, and we can classify action if they have both property. Namely, okay, if I have time, I will certainly define that. So you know that UHF algebra is sort of Elliott classifiable CSR algebra. So therefore, we can define an action which simultaneously both has the Rocklin property and approximate representability just by using left regular representation. This matrix exactly comes from the left regular representation. But on non-classifiable CSR algebra, or better to say in some CSR algebra with non-zero radius of comparison, we cannot define an action such that simultaneously the action has the Rocklin property and is approximately inner. And even in general version, we prove it for general version. So therefore, those actions can be only defined on Elliott classifiable CSR algebra, which has both property. So at the same time. Yeah. Oh, okay, this one. Oh, you can see it? Okay, great. Oh, thank you. So here, definition, Phillips 2011. Let A be a C-star algebra. Okay, here we need more, perhaps simple plus unital plus infinite dimensional C-star algebra. And let alpha be an action of G on A. Then we say that, okay, now here, we say that alpha, okay, alpha has the tracial Rocklin property. If for every epsilon bigger than 0, and every finite set F in A, and every positive element X with no 1, there are orthogonal projections, e.g. G in A for G in G, such that, okay, with E is equal to the sum of EG, the following holds. Number 1, okay, alpha G, okay, let's write like that. A EG is close to EGA for all A in A, F, and for all G in G. A approximately commutes with EG. Number two, alpha G of EH is close to EGH for all G and H in G. Number 3, 1 minus E is Kuhn subequivalent to X. So this means that for every eta bigger than 0, there exists a sequence xk 1 to 1 in A, such that the norm of the limit of xk, okay, xk 1 minus E xk star is equal to X. So, and number 4, the norm of EXE is bigger than 1 minus epsilon. So actually, as you see, the first two condition is exactly as same as the condition 1 and 2 in the definition of Brooklyn property, but here we have further definition. So we call it tracial because this condition can be replaced by tau of 1 minus e less than epsilon for all trace in tau of a. And that's why this is called tracial Brooklyn property. So, and now let's I think that we have simplicity and infinite dimensional or something. First of all, from here to here is obvious. Yeah, but x should be chosen very, very small. And perhaps in that case, we need a strict comparison. Yeah. But, yeah. Yeah. But this is, I think that this is the reason that why we call it tracial. So, yeah. And now, okay, and in the definition of weak tracial Rocklin property, so here the definition motivated by Hirschberg and Horwitz in, I think that 2013. And here again, we have a simple unital system algebra, and then here alpha has the weak tracial Rocklin property. And if again, for every epsilon bigger than 0, every finite set, every x, but here instead of orthogonal projections, we have positive contractions. Okay, let's call it FG. And then here again, F is equal to FG. And then instead of EG, we use FG. And again, here in this definition, we use FG is alpha G of FG is close to FGH. And here we have F. And here instead of E, we have Fx, F bigger than 1 minus epsilon. Now,
and also anything about orthogonality or almost orthogonality?
So I think that you can, so here, okay, here we can certainly say orthogonal, okay.
Yes, then in some
orthogonal,
conditions.
yeah, it is necessary. Thank you for catching it. Yeah, but we can, I don't know, we can instead of saying orthogonality here, we can have approximate orthogonality, stuff like that. Here is easy. So, so one might ask, okay, whether you already defined this definition of, I don't know, weak tracial Rocklin property, but one might ask whether there exists an action, a finite group, which has a weak tracial Rocklin property, but it doesn't have a tracial Rocklin property. And to answer this question, we provide this example. The example is let Z be the Jiangsu algebra. Okay, is it visible or maybe? Okay, just briefly. And let alpha from zima to z to morphism of now z tensor z be the flip action. Be the flip action. Now this action has a big tracial Rocklin property, but it doesn't have the tracial Rocklin property, and it's because of the property of John's algebra. It's sort of projectionless CSR algebra. So now it's time to let's use this one. Definition. Phillips 2011. Okay, let A be a unital CSR algebra. Okay, and here we have simplicity plus unital and plus infinite dimensional. So, and let alpha be an action of G on A, be an action. Yeah. We say that alpha is tracially approximately representable. Okay, and we call it T. Okay, tracially approximately representable. If for every epsilon bigger than 0, for every finite set F in A, and every positive elements X in A with norm of X is equal to 1. There are a projection. There are a projection E in A and a unitrace okay, but now our unitrace WG in the countdown of A, not in A. For G in G, such that okay, number one, okay, E commutes with all elements A in A approximately for all A in F. Number two, Now, alpha G of EAE is close to WG E AEWG star for all A in F and for all G in G. And number 3, WH is close to WGH for all G and H in G. Number 4, alpha G of WH is close to WGH G inverse. Number 5, 1 minus E is cons sub-equivalent to X in A. And number 6, norm of EXE bigger than 1 minus epsilon. So this is the definition of tracial approximate representability. So now, theorem. Theorem. Phillips 2011 proved that let A be a unital plus simple infinite dimensional C-star algebra, and let G be an abelian finite group, and suppose the cross product of G, A, and alpha is simple, then number 1, alpha has the tracial Brooklyn property if and only if alpha hat is tracially approximately representable. Number 2, alpha is tracially approximately representable if and only if alpha hat has the tracial Brooklyn property. So now it's time to define the weak tracial approximate representability. Here is the definition. Where is the definition? Now, here, 2021. So again, let A be a simple unital, okay, good C-star algebra. Then here we say that alpha is weakly tracially approximately representable, and here we call it weakly tracially approximately representable. Okay, here again, for every epsilon bigger than 0, every F whatsoever. So here, instead of projections, we have contractions. We have contractions SG. Okay, no, we have an element in the, let's call it C, in the fixed point algebra, and also the norm of C is less than 1. Okay, and this is supposed to be positive. And instead of unitaries here, we have contractive. We have contractive elements. Elements SG. SG in, now instead of unitary of the cut down of A, we have this one, the cut down of A, but now by C, and then closure, such that, okay, such that, first of all, here we should replace E with C, and again here with C, and here instead of all A in F, we should add also SG, such that G in G. And then here, alpha G of A, E, here we should multiply by C. And here we have SG, A, SG star. And then this situation, this condition is replaced by SG, SH is equal to C, SG, SH. So we somehow get a homogeneous elements. And then here alpha G of SH is close to STH. And here instead of E, we should use C, here C, here C. But here we have one more condition, condition 7. Condition 7. S1 is supposed to be close to C, and also SG star is supposed to be close to SG inverse for all G in G. And then what we prove, okay, here we prove that, okay, let A be a unital simple Tracial algebra and let G be a finite abelian group. And here, instead of simplicity, we can say that alpha is pointwise outer. Then if alpha has the weak Tracial Approximate property, then alpha hat is weakly tracially approximated representable. And if alpha is weakly tracially approximated representable, then alpha hat has the dual action has weak Tracial Approximate property. So I think that I'm actually out of time, but just 5 minutes. So just to say something about the radius of comparison of the cross product by this kind of action. So so just briefly, if we have an action of theorem, theorem A21, let alpha be an action of G on A and be an action. But not here, G is not necessarily a billion. And A is again simple unital infinite dimensional. And if alpha is weakly tracially approximately representable, then number one, RC of A is less than RC of the cross product G, A, and alpha. And if number two, if the cross product G, A, and alpha is simple, then RC of A RC of A is less than RC of the cross product of G, A, alpha, and this is less than or equal to RC of the fixed point algebra. So, and just brief definition for radius of comparison. Radius of comparison is just a numerical invariant. So, and this is defined based on the cone semigroup and trace on A. So, and then putting this theorem. Actually, I should mention that we have this version of theorem before. It was part of my PhD dissertation, but we proved it by a version of tracial version of approximate representability, but we generalize it here by weakly tracially approximate representability. And then as an application of this theorem, we can prove that if we have an action, if we have a CSI algebra such that RC of A bigger than 0 and less than infinity, then there is no action of non-trivial finite group on A such that this action simultaneously is weakly tracially approximately representable and has the weak tracial Rocklin property. This is just as an application. This is just the application of this theorem. And this is, and also here, one thing that I forgot to mention is that we can also weaken this assumption to get this term. So namely, this condition is extra. So this condition can be omitted, condition 4, and then we call this kind of action is weakly tracially strictly approximately inner. So it is somehow complicated definition, but it's just because all people choose the name of some actions, so and we couldn't find the appropriate definition. That's why we call sort of action very complicated setting. So that's all, and I'm ready to be asked by any question. Thank you.
We have a comment that says very informative. Thank you very much. If you're in the audience and want to ask a question, feel free just to unmute yourself. I'll ask anyone in the local audience if they have any questions.
Yeah, so can I ask something? Can you hear me?
Yeah.
Yeah, so I just wanted to ask, how about infinite groups? I mean, I understand that you said that there are some problems with definition for compact abelian groups. But how about if you consider some compact groups which are, I mean, very close to finite, in the sense, for example, for finite groups, which are inverse limits of finite groups. Yeah. And then the Pontryagin duals are the direct limits of finite groups. So maybe.
Yeah. Yeah. Okay. First of all, I should ask you. Okay, you are asking about this result about the radius of comparison, or no, the duality result.
Yeah,
so
the duality result.
Yeah, the duality result. The problem is that the right definition of Tracial-Rocklin property for non-finite compact group is not defined yet, and I know some people are working on that, but nothing is known about that definition. But first of all, we get this result in the setting of compact group here exactly, and the work is in progress for the result about the radius of comparison if we choose if our group to be taken as a discrete group. So, and also with the approximate representability. So, and our result about the application of this theorem is also true for discrete group, and it is also work in progress.
Okay, thanks.
So but I'm saying that the most, not the most, but the general setting about the duality is just introduced by Ball-like, Szabo, and Voigt in co-exact compact quantum group. But the point is that they define something like spatial Rocklin property. So, and as I said, the problem with Rocklin property is that even our groups are compact. The problem is that Rocklin property is rare. So certainly, it's really, that would be a nice question if we, for example, find the right definition of Tracial Rocklin property on non-finite compact group, and then consider the duality theorem about that. But I think that it is work in progress as far as I heard around. It is work in progress, the definition of Tracial Rocklin property for non-finite compact group.
Yeah. I mean, certainly, I mean, it's not clear how it should be the definition for, I mean, general compact groups, for example, for connected compact groups. But I mean, for some special cases like these profinite groups, I mean, which are inverse limits of finite groups, I mean, there are some, I mean, some obvious candidates. So for definition, so maybe I will ask you later. I mean, they will tell me if it makes sense or not.
Yeah. Okay. But you know, to get the appropriate definition, you know, everything should be you know, set together. For example, if you get suppose that you define a definition and you think that this is an appropriate definition for Tracial Rocklin property for non-finite compact group. So the first thing that you should try is that, okay, regardless of duality theorem, you should try, okay, can we, for example, if our action has this Tracial, I don't know, Rocklin property, and A is simple, does it imply that the cross product is also simple, and some other things should be checked? And then if all those properties arrange together and fit together, then you can think that, okay, this might be an appropriate definition for Tracial Rocklin property for non-finite compact group. And then in the next step, it is really good question to think about the duality theorem. Yeah, I mean that the key point to I think that the first step to answer this question is what is the appropriate definition of Tracial Rocklin property for non-finite compact group. This is the first step.
Yeah. Okay. Thanks.
Yeah. Thank you. think that there is a question. So there is a question. Could you please explain which property of the action would imply the other one? So, for example, Rocklin dimension 0. Okay, yeah, this is sort of things that I think that I should have even mentioned that, yes, if we have a Rocklin dimension 0, then our action is has the Rocklin property, and vice versa. If our action has the Rocklin property, then the Rocklin dimension is 0. The same is true for approximate representability. Namely, if our action has a representability dimension 0, then our action is approximately representable, and vice versa.
Representability, some type of is for a Rocklin dimension.
So you mean that representability dimension?
Yes.
No, the representability dimension is already known, and it is a part of the work of Gardella, Hirschberg, and Santiago in 2021. So it's already known, yeah. So it is not part of my result. So yeah, but one thing, so I didn't have time to explain here, but certainly if we have a finite representability dimension, and or CSR algebra has sort of nice property like the radius of comparison is 0, then our action has is weakly tracially approximated representative. So it's sort of dual things, because we also have this thing for weak tracial Rocklin property. If we have a finite Rocklin property, RC of A is 0, extremal trace are finite and whatsoever, then this implies that alpha has the weak tracial Rocklin property. Yeah. Any other question?
Any other questions?
Yeah.
So just to follow up about pro-finite groups. I mean, are there any actions of pro-finite groups that are known, for example, on the infinite transitory algebras itself? Like, are there any interesting examples that might be considered that you could, and perhaps it's known the cross product is simple, for example?
Oh, well, with which property? Rocklin property or weakly tracially representable? Or
do you have any idea of an example of an action of a pro-finite group, for example, on the infinite tensor product of the Jiangsu algebra with itself, that you might be able to check the cross product is simple?
Oh, okay. Not infinite tensor product, but I think that something like some example like that is already known by the work of Hirschberg and Orwitz. They construct they construct an action with weak tracial Rocklin property, and the example is exactly the generalization of the example that I wrote here. The flip action, yes, it can be generalized to. So I think that permutation SM or something like that.
So
yeah,
exactly.
So
you could, to generalize this flip to finitely many factors, if you have some group of permutations, like when that whatever property.
Yeah. So this action is this action is, I mean, that this sort of action is already known, and it is in the work of Hirschberg and Orwitz in 2013. Those action has the weak tracial Rocklin property, but they don't have a tracial version of Rocklin property. And therefore, when we have this action in the abelian setting, the dual of them is weakly tracially approximately representable by the theorem that we already proved here. But now it's really good question to construct the example of a finite non-abelian group such that the action is weakly tracially approximately representable. And so I couldn't construct this kind of example yet. But we already have some example, but it comes from the dual. But it's really worse and good if we could construct the example on non-abelian group directly. Yeah. Rather than using the duality theorem here.
Okay, well, we've gone. I don't think there's too many other questions in the chat. So maybe we can just thank Ali again, and then us locals might continue chatting a bit.
Okay.
So thank you very much, Ali.
Yeah, thank you. Thank you for having me. Thank you.
And if I can just quickly advertise next week's talk, if people are still here, which I have seemingly accidentally lost in my screen. Just a second. Nope. Oh, sorry. Okay, so next week we have Giancarlo Taboida from the University of Warwick, who has the rather intriguing title of the non-commutative Riemann hypothesis. So I hope that should get people interested, and we'll see you on Zoom next week. Thanks.